Hello, everyone. Thanks for coming. First of all, safe harbor statement. I'm an architect. I'm not in product management. I'm going to talk about some stuff that we're working on. It may never make it into the product. I hope it does. But some of the stuff here is just a glint in people's eye, so don't assume that this is necessarily going to be delivered. I hope the purpose of this talk is you'll understand what the problems we're thinking of in engineering, how we're approaching them, and some possible ways of making Looker better and smarter. So we're getting a bit close to lunchtime. You guys need to be, I thought you guys need sharpening up a little bit, so I've got a little math problem for you. And since we're getting near lunch, it's related to food. So we're going to buy 3 ice creams, and each ice cream costs $1.50. And each topping costs 50 cents, and each ice cream comes with a topping. So how much do 3 ice creams with toppings cost? Anyone have an answer? $6. Good. So the question, actually the bigger question is, how did you do it? Did you say $1.50 plus a topping is $2, multiply by 3? Or did you say 3 times an ice cream is $4.50, 3 toppings are $1.50? Which one did you do? Okay. Why? Easier, yeah, exactly. So we know that they're the same, they give the same answer, right? But our little brains go, multiplication is hard, addition is easy. I'm going to do the way that does 1 multiplication and 2 additions, okay? So you did some algebra. I hope everyone else in the room did some algebra. So in mathematical terms, that uses an algebraic identity, which is you can multiply numbers together first and then add them, or you can add them and then multiply them, and it gives you the same result. And intuitively, we use the way we use the algebraic identity so that we do less work. And this is what a database query optimizer is trying to do. So this example is in high school algebra or arithmetic algebra. So what does the word algebra mean in general? It's a mathematical language for combining particular quantities. A set of operators. In the case of arithmetic, it's the plus and multiply operators. And some algebraic identities, which are ways you can transform those equations that still give you the same answer. And those algebraic identities we call rewrite rules. It's a way of changing the equation into something else that means the same thing. So having introduced algebra, here's another kind of algebra, and this is the kind of algebra that I work with on a daily basis, called relational algebra. And the quantities in play there are relations. A relation is a word for a set of records. You can think of a SQL table as a relation. The operators are things like join, union, filter, and there are algebraic identities as well. So for example, if you have a relation and you union it with the empty set, you end up with the original relation. That's the equivalent of adding 0 to a number in ordinary algebra. More complicated is if you take 2 relations and you join them together, and then you union them with the 2 other relations, that's the same as doing the union first and then the join afterwards. So let me give some examples. And these, the top line of this slide is how you'd represent it in algebra. Below it is the equivalent thing in SQL. And frankly, it's a lot easier to understand in SQL. So the left one is saying we have a products table. We have 2 orders table, one which is last year's orders, one which is this year's table. We can union the orders together and then join it to products. Or we can join the products table to the orders in each particular year and union the results afterwards. And that one, if you kind of squint, that equation there is very similar to the equation that we used for the ice creams, right? So it's a kind of an analogous equation where union is the same as plus, join is the same as multiply. The second one, this sigma operator means filter. In other words, it's a where clause. We can take products, find all the red products, and then take the result of that and filter where it's a type of bicycle. Or we can combine both conditions simultaneously. Red bicycles. So, and that's an example of basically combining two filters into one filter. So you've now learned two algebraic rewrite rules. These are the things that power query optimizers in, for example, Oracle or BigQuery. Relational algebra is what we're interested in Looker. Because Looker's goal is to write better SQL than you can, or in fact, to prevent you from ever having to write SQL. So we want to make Looker smart. Relational algebra is this mathematical theory that's used in industry, certainly in the database world, that allows us to optimize queries. And we can use this, we can bring this into Looker and make Looker smarter, which means that you have to write even less SQL than you had to before, or the SQL that you do write or the queries you do write will run faster. So that's what this talk is about. I've already introduced relational algebra. I'm going to dive into some internals about. And by the way, this is kind of more for your education. This is maybe not relevant to how you use Looker, but I think you'll just find it interesting to know what we're doing. I'll talk about a couple of features that we're working on that this makes possible. So a little bit more about relational algebra now. The technology we use to do this is called Apache Calcite. I founded Apache Calcite in 2012. I've been working on it ever since. And Looker hired me about 18 months ago because of my expertise in Calcite, and we're now using Calcite inside Looker. What Calcite is it's kind of a framework for building a database. It's not a database itself, although you can kind of use it as a virtual database. But it has an engine that does query planning. It's used in a lot of other products and projects. For example, it's an Apache Hive. Apache Hive uses it as its query optimizer. It does work standalone. There is a SQL parser and a JDBC driver. It doesn't store its own data. So when you use it in that mode, it's going to connect to other data sources. And it's under the Apache Software Foundation. So we use the Apache development model where basically anyone can contribute regardless of who their employer is. And when people are working inside Apache, they basically leave their corporate affiliations at the door and they agree that they're going to do whatever is best for the project. And this is a very productive development model because it means everyone's acting in good faith and people who might be working for competing companies can work alongside each other in an open source project to make the project better. Quickly, here's the architecture. As I said, there's a JDBC client if you want to use it, and a SQL parser. But the core of this is the blue boxes, the operator expressions, which is our implementation of relational algebra, and the query optimizer, which, as I'll explain later, is powered by those rewrite rules that I just talked about. There's optional things like metadata providers. So if it's optimizing a query, there's a way of Calcite asking you how many rows are there in this table? Is employee ID a key? how many distinct values are there for department number, all of that kind of stuff. So, quickly, here's a SQL example, an example SQL query, and how it translates to relational algebra. And by the way, I was using Greek symbols earlier, sigmas and pi and that weird join symbol that looks like a bow tie. I'm not going to use any more of those Greek symbols. I tend to use the English words here because these are the names of the classes in Calcite. So, for example, filter is the sigma operator. It basically is a where clause. So you read this from the bottom up. We start off by scanning the employees table and the departments table. We join them. And you can think of this as a kind of like a Unix pipeline. The data is flowing through these operators. It flows through the join, through the filter, which implements the where clause, all employees who are older than 50. Aggregate is group by. We apply another filter. That is the having clause. So we can only apply that filter after we've aggregated and figured out what the count is. Then we project, which is the select list. And finally, we sort. So that kind of gives you, I think there's about 6 different relational operators in that. The thing about relational algebra and SQL is there's it's kind of good cop, bad cop. It's difficult to implement it. You have to have a SQL parser. You have to have an optimizer. You basically can't execute this stuff directly. That's the bad news. The good news is once you have an optimizer, now you have an awful lot of flexibility in terms of how you structure your data. If you have a relational database, you can add an extra index and the query will use it, even though you didn't change your query. So once you've gone to the effort of adding an optimizer and gone through this intermediate layer of relational algebra, all of a sudden you have a lot more flexibility. And as you'll see, we're trying to bring some of those values into the internals of Looker. Here's an example of an algebraic rewrite. I'm going to replay this slide a couple of times so you can see. So the filter, we're applying a filter age greater than 50. And we apply it after the join. And if you think about it, because that filter only applies to things from the employee's side of the join, it would be more efficient if we do that before the stuff goes into the join. So we apply this rewrite rule that says you can push a filter through a join and it produces equivalent results. So that's what the optimizer does. It applies this rewrite rule. Now, actually, in Calcite, there's probably 200 rewrite rules, and you can write your own. And what the optimizer engine does is it applies those rewrite rules guided by a cost model that gets it towards something that has the lowest possible cost. But the individual rewrite rules actually are not cost-based. The rewrite rules are, it's an algebraic identity. It's either valid or it's not valid. You can't say, oh, this is valid if it's, the cost is greater than 100. No, this is always valid. And some of our rewrite rules sometimes make things better and sometimes make things worse. And the engine's job is to figure out when to apply them anyway. Calcite is a framework. It's written in Java, which means there's a whole bunch of classes. And you can basically pick up this. It's a pretty big API and use it to build your engine. And that's what people like Apache Hive, Apache Beam have, and lots of companies have basically picked this up and embedded Calcite in their product. And this is what we are doing with Looker. Okay. So we're going to talk about how Looker internals work and how we're bringing Calcite into that query preparation process. So this is a complicated diagram of Looker's architecture. It actually shows both it's the flow from the left-hand side when we receive a Looker query, perhaps from a dashboard, perhaps from an Explore, to the right-hand side where we've generated some SQL and we're ready to go send that to the database to get the results. And as you can see, there's a lot of steps involved. This diagram is a little bit complicated because it shows both the old way we were doing things and the new architecture that we are in the process of putting in place. And actually, I want to give a shout out to Stephen Talbot here. Maybe you attended his talk yesterday. Stephen's doing a lot of the work pushing Looker internals to this new model. Not right now, obviously, but so the old way of doing things, we had we would compile the query into a data structure called htQuery, and then we use a dialect object that tells us about the capabilities and syntax of the target database, and a writer that converts this into a SQL statement. We also talk to the PDT service. A persistent derived table is a table that's basically computed, populated on demand. And if the query uses that, then we talk to the PDT service to find out the name of the actual physical table in the database to substitute into the query. In the new way of doing things, it's still the basic flow, but we've added Calcite as an intermediate step. So what comes out of htQuery, which is this data structure that represents a parsed query, is we go into relational algebra, Calcite relational algebra. We use Calcite, and we've also made some internal extensions to Calcite. And from that, we go into, basically, Calcite has a parse tree, which is what would come out of a SQL parser, but we're running the process backwards. So we produce a SQL parse tree, and then we can convert that SQL parse tree back to SQL text. The other added thing there is aggregate awareness, which I'm going to talk about later, which is this ability to modify the query and use aggregate tables, also known as summary tables, in order to make the query more efficient. And aggregate awareness is one of the big things that was motivating us to introduce Calcite in the first place. So, aggregate awareness. Who's heard of aggregate awareness? Who knows what this term is? Okay. So maybe a third of you. Well, you will know what it is in a minute. So let's take a simple example. We have a customers table with 12 million rows and an orders table with 100 million rows. And we're interested in, and this is in the United States, so there are 50 states. We're interested which state had the most revenue in 2018. So in order to do that, we'd have to basically scan 100 million rows, join it to a 12 million row table, do a big group by, produce 50 rows, and then basically, well, sort them in descending order or something like that. Let's suppose we've cheated and pre-computed a table with 2,000 rows, which is sales grouped by state and quarter. So 4 quarters, 50 states, perhaps a much smaller number of rows of data. We can compute, the tables are synchronized, so we can compute the same result. We will get the same result, but it's a lot less effort to use the aggregate table. So this is kind of tantamount to cheating. I mean, I have some friends who are in the programming language community, and they're pretty pleased if their program optimizer can make the program run 10x faster. In the relational database world, these kind of query optimizations can produce results millions of times faster. It is just by essentially you're cheating, right? It is just astonishing how much faster things can be if you've pre-computed the result. The tricky part is knowing what you should pre-compute and knowing when it's safe to use that pre-computation. So some people use aggregate awareness in LookML already. This is what they do. If you've got, let's say, an orders explore, which is based on an orders table and a customers table, they will go ahead and produce this orders summary table, orders by state and quarter summary table. And they make it a derived table, so it's basically pre-computed. The problem is that you only get to use that if you use that explore, the orders by state and quarter explore. You don't get to use it if you're just using the orders explore. So what we mean by aggregate awareness, and I'll explain how this is possible, is how you automatically use this summary table when you're using the orders explore. Some database terminology. These are the words that folks in the database research community use for these things. These are the words that if you're reading the manual of Oracle or DB2 or BigQuery, they're going to use words like this. These are the same concepts we're working with. These aren't the concepts, these aren't the words we use in Looker. But this is, these are the concepts. So a view, as in a create view statement, is a table that expands to a relational expression. I'll give you some examples of this later. A materialized view is similar, except it actually has a physical table. So it's defined by a relational expression, but it actually has a concrete data set that's stored. And as we'll see, a materialized view and a view are kind of almost opposites of each other in terms of how they're used. An aggregate table or summary table is a kind of materialized view, but it's based on a group by and join, which is the most important query pattern if we're working in business intelligence. And aggregate awareness is this ability to automatically use aggregate tables. So let's just run through quickly what happens when a query uses a view. I'll just say again, this is not what Looker means by it. This is not a view in Looker terms. This is what Oracle or DB2 or BigQuery means by a view. So we have a query that uses a manager's view, and at the bottom we have the definition of the manager's view. Now let's look at this in relational algebra terms. The query has a scan of something called managers, which the query thinks is a table, but actually managers is this blob of relational algebra. And when the system is preparing that query, it says, aha, they've referenced managers, I'm going to substitute in this blob of relational algebra. So the query, after it's been prepared, is now this combined piece of relational algebra. And perhaps it can be optimized. So we've got a filter, age greater than 50. That filter can perhaps be pushed down. So I think people who use views in relational databases know that even if the view returns 1,000,000 rows, that doesn't mean that the query is necessarily going to process 1,000,000 rows because it pushes conditions and things like that down. Now, a materialized view, the definition looks pretty similar. We've got a materialized view, employees by department and gender. So it's a group by query. It has many fewer rows than employees. Here's a query that doesn't reference the materialized view. It just references the employees table. But we would like it. It's beneficial to use the materialized view, and it is possible to. So the hard part, and this is the this is the stuff that's going on in Looker, in a future version of Looker, is to basically unify these two things. To notice that I can rewrite my query that uses employees to instead use employees by department and gender. And what it has to do is prove that the query, the expression that defines this materialized view is a, what's the word? A subset of the query that they actually asked. So in order to do that, we actually have to rewrite the query, move things around so that the expression that defines a materialized view is the same as this expression inside the query. When we've done that, we've struck gold, and now we can safely substitute in the materialized view. And now we have a query which is more efficient because it's using a summary table. Okay, so this is basically the same slide as before. The difference is that when this feature that we're working on makes it into Looker, you will be able to use this Orders Explorer on the left-hand side, and it will automatically use your summary table. So you can kind of throw away that Explore orders by state and quarter. You can just work on the raw Explore. Okay. So here's another thing. We've got many features we'd like to do. I'm just going to describe one more thing that's this makes possible. And by the way, since we're right before lunch, we probably won't have time for questions, but I'd love to speak to folks directly after this and hear how you think this stuff could be used. So let's suppose you're a company that's just started using Looker, but you've been using some other BI tool, or perhaps you've been writing SQL manually. There's a lot of value locked up in those queries that you've run in the past. Because you've just started using Looker, you don't have any LookML yet. But suppose we could look through those queries. Could we detect what your dimensions are, what your common join paths are, what your measures are? And the answer is yes, we can, or at least we hope to be able to, because we're working on this. So if we parse through the SQL queries in the log, we can recover that information and generate a kind of a first cut LookML for you based on the queries that you've run. We already have a model generator, but it's kind of structural. In other words, it looks at the names of the fields. This one is a kind of a different approach, a complementary approach to that, that looks at the actual queries that you've run. We call this process model induction or perhaps model generation. This LookML model is, one of the possible uses of this is your users may not have written a lot of LookML. Perhaps this LookML model can be a good teaching tool if they can kind of see some of the patterns that we've, how we model the patterns that they've put in their queries. So how do we do it? Here's a pretty complex query with, it's got an in subquery, several joins, several aggregations, some aggregates on expressions, so sum of revenue minus cost. A lot of relational algebra. So Calcite uses its SQL parser. We actually have a variation of the SQL parser that's can handle other dialects of SQL besides Calcite's dialect of SQL. And what we focus on are the table scans and the joins. The in clause becomes what we call a semi-join. It's a special kind of join. And we notice that we're joining orders to customers and then to order items, and then we're using a semi-join into some query which is based on products. And what we construct is a join graph, which is what tables are we using and how are we composing them, what foreign keys are we using to combine these things together. And also, what measures are we using? In this case, one of the measures is based on an expression. So we do this for a lot of queries. On the left-hand side, we've got a query file with 4 simple queries. We've identified that the first query joins orders to customers, the second query joins products to orders, and so forth. So we're producing that we've got 4 separate join graphs for each of those queries. The third step is to kind of meld those join graphs together. And what we've done is we've combined them into 2 different join graphs. And what they have in common is one of them is based around the inventory fact table, which is, so each of these join graphs, these merged join graphs has a central table. And the second one, inventory is the central table, and the first one, orders, is the central table. And then we generate LookML, and each of those join graphs becomes an explore. The first explore is based on orders, and the second explore is based on inventory. Okay, I think that's all we have time for. Thank you all.